thank you everybody for coming and to the defense for Garima Malhotra. And Garima has been a graduate student at U of M for a few years now and has been working on ionosphere, thermosphere modeling stuff, as she will talk about. And yeah, we have even more people showing up as we're doing this. This is great. This is the format that we're going to do today is basically Garima will talk for around 45 minutes, and then we'll have people in the audience ask questions, and then we'll go into sort of a closed session where we'll ask everybody to leave, and then the committee members will ask questions at that time. And so we're basically not going to ask any questions during her presentation unless it's like a clarifying question or something like that. And then at the end, we can ask more questions. Anything else that I'm missing? I don't think so. Okay, so with that, Garima, do you want to go ahead?
Yeah, thank you so much. I would like to begin by thanking everyone for being here. I appreciate this a lot. I know this is a difficult time for everyone, and last year has been crazy, but we got through this. And like I had never imagined, like a few years ago, that this is the way I would be defending my oral thesis. Yeah, everything is unexpected, and I'm glad that here we are. I would like to thank my advisor, Ridley, for being extremely supportive and being responsive and replying to my questions and emails very promptly, especially in the last year. Thanks to my committee members as well for their helpful comments. My family. I wanted to invite my family to this call, but then I realized that it's just going to be too much pressure for me. So I decided that I'll just share the recorded version with them later on. And I would also like to thank Faye, Brian, Darren from the IT department of CLASP. Yeah, I have had like long chains of emails going on with them, and they have always been extremely patient and responsive. I would also like to thank, acknowledge the university and the lovely city of Ann Arbor. It's my whole experience in this grad school has been extremely nurturing, and I'm glad that I chose University of Michigan for this. So the focus of my thesis is to understand the coupling between the lower atmosphere and the upper atmosphere. And the way I do that is by looking at the coupling of the transition region, which is the mesosphere and lower thermosphere, with the upper atmosphere. So this is the outline. When I started making this presentation, I immediately wanted to just jump to the results of my studies, but then I realized that it would be really weird if I do not introduce most of the terminologies and basic concepts of what I'm going to talk about. So I'll start with a brief introduction. So as we know, Earth's atmosphere is extremely thin layer of gases. We live on the surface, but above us is the troposphere, and we live in the troposphere. This is the layer where most of the weather phenomena occur, where we see clouds and rains and precipitation. This extends till about 10 kilometers. Above that is the stratosphere, in which we have the ozone layer. And the ozone layer is extremely important because it protects us from the ultraviolet radiation from the sun. It extends up to about 50 kilometers. For better perspective, Mount Everest, the peak of Mount Everest is at about 9 kilometers, which is the upper limit of troposphere. So that's why people have a lot of trouble breathing up there, because you are breathing in an extremely thin air. Above that is the mesosphere. Mesosphere is an interesting region to study because there are not as many observations. So troposphere and stratosphere can be very well studied using weather balloons or using aircrafts, but mesosphere is too high for weather balloons and too low for satellites to orbit. So most of the observations in mesosphere are basically from rocket-borne instruments or remote sensing. Above that is the thermosphere and ionosphere. Starting from this altitude region, we basically categorize everything as the upper atmosphere. The thermosphere and ionosphere is even more interesting because now we not only have neutrals, but we also have ions and electrons interacting with electric and magnetic fields, which make this region even more complicated and dynamic. Above that is the exosphere. There is no demarcation or no upper limit of exosphere. It's basically the entry into the outer space. The thermosphere and ionosphere is the focus of the study from about 100 to 600 kilometers. This is the region. And this is particularly interesting also because this is the region where we have LEO satellites, where we have International Space Station. So this is not a stagnant region. It interacts with lots of other variations as well. So here I show just the temperature profile of the atmosphere. So from about 0 kilometers to 600 kilometers. And we can see that the way we define these layers is basically by these inflection points in the temperature profile. In the troposphere, the temperature decreases, it increases again in the stratosphere, decreases again in the mesosphere, and this is the coldest point. I guess this is the coldest region in the Earth's atmosphere at about minus 100 degrees Celsius. And above that is a thermosphere where temperature continuously increases, and hence the name thermosphere. Another way of looking at the vertical profile of atmosphere is looking at the density. So as we go up, the density decreases. Here at the surface, we have huge number of molecules above us. So the pressure is pretty high. This is the vertical profile of pressure with altitude. So we have lots of air molecules above us, the pressure is pretty high. But as we move up, the pressure decreases. And the most interesting thing about this plot here is look, just how fast the pressure decreases. As at about 5 kilometers above the surface, we are already above 50% of the atmosphere. If we someday reach the peak of Mount Everest, we'll have about 70% of the atmosphere beneath us. And by the time we reach 30 kilometers, which is the stratosphere, we have 99.9% of the atmosphere below us. So we can basically say that the thermosphere and ionosphere, which starts from 100 kilometers, the densities are extremely low, and that's why it's categorized under space physics. And let's look at the composition of the thermosphere and ionosphere. The most important line plots here are the green line and the blue line. The green line is the atomic oxygen and blue line is the molecular nitrogen. So as we move up at about 200 kilometers, the molecular nitrogen stops being the dominating species and atomic oxygen takes over. And this is important because this kind of forms the crux of my first two studies. So densities are extremely low, but they're still enough to cause drag on satellites and for us to worry about them. Let's look at the electron density profile of the ionosphere, which exists in the same altitude regime along with the neutrals. The electron density profile also has certain inflection points, and that's why it's also divided into different regions. I won't be going very deep into this because this does not concern with my results. Next, let's talk about some of the variations in the thermosphere and ionosphere. As we talked about before, this region is dynamic and it interacts. So the most important forcing in this region is from the sun. Sun can lead to short-term and longer-term variations in this region. One of the most important long-term variation is the difference in the temperatures. between solar minimum years and solar maximum years, the temperatures in the thermosphere increases from about 500 degrees Celsius to about 1000 degrees Celsius between the solar minima and maxima. And for a better perspective, the hottest temperature ever recorded on Earth is about 57 degrees Celsius in Death Valley in the United States. So yeah, thermosphere is hot. And one of the examples of the short-term variation would be the aurora borealis that we see at high latitudes, very dynamic as well. So apart from forcing from above, forcing from below is the main focus of the study. There are a lot of perturbations going up into the upper atmosphere through the transition region of mesosphere and lower thermosphere. And apart from these waves that propagate up, we also have turbulence resulting from small-scale structures in the mesosphere and lower thermosphere that also affect the state of thermosphere and ionosphere. So overall state of the upper atmosphere can be described as background plus some perturbations. And it's a highly nonlinear and dynamic system with varied components interacting with each other on different spatial and temporal scales. This is just to overwhelm you. And these are only the neutral equations for the neutrals. The interaction with the ions make it even more complicated. And because it's a nonlinear system, the outcome and total variability of any observable or variable will be far from what you would imagine by simple additive superposition principle. Another quantity that's important in the thermosphere is the composition. So the composition is defined by the ratio of atomic oxygen to molecular nitrogen. And the reason why it's important is because it's directly proportional to the electron density of the ionosphere. And the reason why it's proportional to electron density is because atomic oxygen is responsible for the production of electrons, and molecular nitrogen is responsible for the loss of electrons. So therefore, O2N2 is often used when we say the composition of the thermosphere. So it's not stagnant, as I told you guys before. And the reason for that, at least the large scale variation in the thermosphere is because of the sun, as we talked before. And it affects the neutrals in such a way that we have circulation going on from summer to winter. So this is June and the Northern Hemisphere is in summer. So overall, we have higher temperature in the summer. So this leads to the development of pressure gradients in such a way that the winds start blowing from summer to winter. And this also has an effect on lighter species such as atomic oxygen and helium in such a way that most of the lighter species start accumulating in the winter hemisphere because of the transport by this circulation. And therefore, in the winter hemisphere, the O2N2 ratio, the composition that we talked about, will be much higher. If we look at the December solstice, where winter is in the northern hemisphere and the summer is in the southern hemisphere is in the summer, the winds start blowing in the opposite direction, and O2N2 ratio is higher in this in the northern hemisphere this time. In contrast, during equinoxes, both the hemispheres receive equal amounts of radiation from the sun. So this leads to very weak winds, and most of the background winds blow from equator to poles. So the solstice meridional circulation, meridional is another term that I might use. It just means north-south winds. So yeah, meridional circulation during solstice is pretty important to the study. So I want you guys to remember this. And the reason why I'm studying all this is because any change in the densities can, in the thermosphere and ionosphere, can affect the drag on the satellites, which needs to be compensated by satellites' propulsion system. It can also lead to torques, which need to be controlled by attitude control systems, and uncertainties in drag on the satellites can also propagate through the orbit propagators, which can affect our ability to track their position accurately. This is also important because if there is a geomagnetic storm, the background state of the thermosphere can alter the response of this region to the geomagnetic storms. So most of this study is done during geomagnetically quiet time. That is, we do not have coronal mass ejection from the sun or high UV radiation. It's pretty quiet during this time. And this helps us in understanding the effect of the lower atmosphere more easily. So I'll go ahead and talk about some of the outstanding questions that I encountered when I started this research. So again, the goal is to understand the coupling of lower atmosphere with the upper atmosphere, and through the transition region of this mesosphere and lower thermosphere. The interesting part about this mesosphere and lower thermosphere, I'll also refer to it as the MLT region. So interesting thing about this region is that it's pretty hard to measure. So that's why there's a lot of mystery about densities, winds, and composition in this region. And it extends from about 90 kilometers to around 130 kilometers. It's kind of the boundary between mesosphere and thermosphere. And I will be mainly focusing on the effect of atomic oxygen and turbulence from the MLT region into the thermosphere. So as I said before, it's pretty hard to measure the densities in the MLT region. However, because of the launch of new satellites, such as timed mission, there have been lots of measurements of atomic oxygen in the MLT region. And this helps us in understanding what we did not understand, what we did not understood before. For example, this is what we assumed previously about the atomic oxygen distribution at 100 kilometers, which is the MLT region. This is December, so we have winter in the Northern Hemisphere. So what we see is large atomic oxygen densities in the winter as compared to the summer. Now, when we look at the SABRE data, as we have new observations, we in fact see something opposite. We see that the concentration is higher in the summer. So this was my major motivation when I started this research. I was pretty surprised at how everyone has been focusing on this previous observations and nobody is really asking the question as to why, first of all, why this opposite variation is observed and what are the impacts that this is going to have on our understanding of the upper atmosphere. And another important observation from SABRE has been the gravity wave activity. The gravity wave activity basically tells us about the small scale structures which in the MLT region, and we can see that these variations change with season and also with latitude and longitude. And the previous assumption was basically just that the turbulence is constant across the globe. So I asked these two questions, and that's how I ended up continuing in this research. So my first question will be about the atomic oxygen. I'll come back to the second question later. The first question is, since O is a minor species in the lower thermosphere, but major above 200 kilometers, does its concentration in the MLT affect the upper thermosphere on short or longer timescales? If so, what are the mechanisms? And yeah, this is the first study, to the best of my knowledge, that actually studies this impact. So the methodology that I use is a physics-based model called the Global Ionosphere Thermosphere model. It extends from about 100 kilometers to 500 kilometers. So basically encompassing the whole thermosphere and ionospheric region. Now, this is a perfect model to study what I want to study because it has its lower boundary in the MLT region. So I can use different assumptions in the MLT region and test their effects on the thermosphere and ionosphere. Another model that I use is the whole atmosphere model called VACMX. It extends from the surface to the to 500 kilometers. So it's pretty cool because it takes in like lots of physics and chemistry of the lower atmosphere. The reason why I use VACMX is because the atomic oxygen from the MLT region is much more similar to the SABRE observations. So I'll talk about it in the next slide. So this is the atomic oxygen from our old boundary condition in GitM, basically the older assumption where during winter in the Northern Hemisphere, the densities were higher, whereas the newer boundary condition, when we use the more SABRE-like atomic oxygen, we see much larger densities in the summer hemisphere. And this is huge. So this can help us in studying the impact of this opposite latitudinal distribution. So the largest, I guess the immediate and the most surprising change that I observed in this study was in the older boundary, when the older boundary condition was used in GitM, we saw the winds to be larger from the Northern Hemisphere to equator because of the larger densities in the Northern Hemisphere, whereas when we used the other boundary condition, the newer boundary condition, we saw that the winds were larger from summer to equator. So here the winds are larger from winter to equator, and here the winds are larger from summer to equator. And what this leads to is adiabatic expansion. So all of us have studied what adiabatic expansion is. So if you have an air parcel and the air expands, the temperature of the air parcel decreases. And on the other hand, if the air parcel compresses, it becomes warm. So what ends up happening is that with the newer boundary condition, we see a decrease because the winds are blowing in this direction. We see a decrease in the summer hemisphere, whereas here in the older assumption, we saw a decrease in the opposite hemisphere, which is completely opposite and very interesting. So if we, so basically the newer boundary condition, if we look at the altitude profile for the newer boundary condition, so what I do in this plot is I take the mean around a latitude circle. So you don't see the latitude longitude plot anymore. All you see is the variation with latitude and altitude. And this is where at about 100 kilometers, this is where we introduced the change in atomic oxygen. And what we see is this decrease in the summer hemisphere here and an increase in the winter hemisphere, which propagates up to higher altitudes. And what we then end up seeing is that the hemisphere, which becomes warmer, has an upwelling of the atmosphere, which means that now you have more nitrogen at higher altitudes. Whereas in the opposite hemisphere, there's downwelling, which means now we have lesser molecular nitrogen at the same altitude. And if we look at the O2N2 ratio, the composition, so now we see an exaggerated effect in the O2N2, which is about 50%. So the hemisphere with high O has low nitrogen, so O2N2 ratio becomes pretty high, and the opposite in the other hemisphere. And if we compare our older model and the newer model with satellite observations, we actually see that the newer boundary condition matches better with the satellite observations. So hence proving that using the SABRE-like observation, SABRE is the instrument, SABRE-like atomic oxygen observation actually improves our estimate of the thermospheric state. In conclusion, this is how I would like to summarize this study. The atomic oxygen changes the equator winds, which changes the temperatures, which changes the molecular nitrogen, which affects the O2N2 ratios, which will also have an effect on the electron density because it is directly proportional to O2N2. If we look at both summer and winter hemisphere, we see the opposite effects. And what ends up happening is overall in the summer hemisphere, the temperature decreases, and the summer is when we have high temperatures. And in the winter, we have low temperature, but because of O, now we have an increase. So the gradient between the two hemispheres decrease because of this lower boundary condition. And same goes for O2N2. So this is pretty interesting as to how something at 100 kilometers can affect the whole thermospheric state. I will now move on to the results of the next study. This talks about the impact of the atomic oxygen variation that we just learned about. So the variation of that and impact of that on the semi-annual oscillation. And again, we use the same model to study this impact. So I hope you guys remembered this plot. So during June, when the northern hemisphere is in summer, we have winds going south, whereas during equinox conditions, we have weak winds. So what ends up happening is during solstices, we have more mixed atmosphere, which means we have more nitrogen in the thermosphere during this time. Whereas we don't have as much nitrogen during equinoxes. And this is all because of the temperature gradient that is introduced by the solar radiation. So if the nitrogen is higher during solstices, the O2N2 ratio decreases during this time. So this is the change in O2N2 with month of the year. So during solstices, during June and December, these densities decrease. Whereas during equinoxes, we have relatively larger O2N2 ratio. So this is called the semi-annual oscillation because it has 6-month period and it is an internal thermospheric mechanism. But there is also a lot of literature about its contribution to the impact from the lower atmosphere. So the contribution of the lower atmosphere. And it makes sense because the lower atmospheric, as we just saw, the atomic oxygen actually plays a really important role in changing the dynamics, winds, pressure gradients. So it should depend on the lower atmosphere as well. Now, the question that I posed was, so now we have the opposite latitudinal distribution that we see in the SABRE data and VACMX. So what happens if we change, what happens to the SAO? Because it's pretty important to get that right as well. So this is the older boundary. This is the newer boundary. As we saw before, so this is the day of the year. So around June, in the older boundary condition, the winter hemisphere had larger densities. Now the newer boundary condition, summer has a larger boundaries. This is similar to what we looked at before in the previous study. And the new VACMX model resembles SABRE data. Here, because of the data gaps, it's not exactly clear, but we do get a good idea that there is a summer maxima in SABRE data as well. Now, the most interesting plot here is this. If we take global means of each of these plots, the blue and the red curves here, blue curve is the older boundary condition, And the red curve is the new boundary condition VAC-MX. The seasonal variation, the variation with day of the year is opposite. So the older boundary condition still uses high densities during equinoxes and low during solstices, whereas in the new boundary condition and the SABRE data, the black line is the SABRE data, larger densities are observed during solstices. So I then decided to run few simulations. The first was with MSIS, which is the older boundary, the newer boundary, which is GETM with VAC-MX. And then I also run 2 other simulations with no SAO at the lower boundary. This is because I want to study, do we even really need an SAO at the lower boundary, or is it just the internal thermospheric mechanism? And the last simulation is using VAC-MX again, but also nudging the dynamics in GETM from VAC-MX. This is because VAC-MX, because it's the whole atmosphere model, it does have better representation of dynamics in the lower thermosphere. So let's look at the semi-annual oscillation in GETM. The black line here is the benchmark. It's from the GUVI observation. It's again a satellite instrument on timed satellite. And the variable that we are looking at here is the O2N2 ratio. If we look at the first simulation, which is basically not having any SAO at the lower boundary, we see very small oscillation. So which tells us that we actually do need an SAO at the lower boundary, and it does play a significant role. If we use the older boundary condition, which is with MSIS, we see semi-annual oscillation with decent amplitude, but it still is far from the observations. Now we use the newer boundary, and what ends up happening is that we see a large SAO, but the phase is completely opposite. And this was shocking, because what we're doing here is correcting the atomic oxygen densities in the MLT region, but at higher altitudes, we are getting something opposite to what the satellites observe. If I look at the another simulation where I nudged the thermospheric dynamics to VAC-MX, I see that the opposite phase decreases a little bit, but it does not reverse completely. And this is another simulation which I tried with more assumptions, and this also showed decrease in the opposite phase. So what's happening here? Let's dive a little deeper. If we look at the GETM simulation with older boundary condition, we see that this equinox maxima and solstice minima, and we see that most of the atomic oxygen is in the winter hemisphere. During June and also during December, most of the atomic oxygen is here in the winter. In the newer boundary condition, the reason why we have this opposite phase is because now we have larger atomic oxygen here at low latitudes near the equator. And same goes for this time as well. So I decided to dive even deeper and understand what's going on. So as we saw before, the temperature gradient between the 2 hemispheres is pretty large. And that is the main driver of the circulation, of the meridional circulation that drives the SAO. With the newer boundary condition, the gradient in the temperature is lower than the gradient in the older simulation. Than the gradient in the simulation with the older boundary. And so this is how I would like to explain this mechanism. So we had the summer to winter winds going on, and this is what we wanted to see, basically decrease in the O2N2 ratio during this time. But what we end up seeing is increase. So this is because of the weak temperature gradient, we have weaker meridional circulation as well. And that is why we see an increase when we use the newer boundary condition. And In this study, I basically tested few more simulations, and I ended up suggesting, and this is an ongoing work, so I ended up suggesting that certain changes in the thermospheric dynamics and using a seasonal variation in the turbulence parameter in the MLT and increasing the circulation can basically reduce the opposite phase of the SAO and hopefully correct it completely. So the summary of the study is basically in this slide. We use no SAO in the lower, in the MLT region, and we get very small variation in the upper thermosphere. As we introduce an SAO with this phase, we get the right phase in the upper atmosphere. As we use more saber-like atomic oxygen variation in the lower thermosphere in the MLT, we get the opposite variation. So use of correct boundary leads to wrong results in the upper thermosphere. So we need additional mechanisms in this region, in the lower thermosphere region, which will help in reversing the phase of SAO. So I would like to put both of these, my first and second studies in perspective so that it's easier to understand both of them. So in the first study, we saw that atomic oxygen has this decreasing effect. So increase in atomic oxygen decreases the temperature in the summer hemisphere. And in the winter hemisphere, opposite happens, right? So overall, we end up with a weak temperature gradient, which leads to weak meridional circulation, which leads to the accumulation of atomic oxygen at lower latitudes. I can also use this illustration. We had higher atomic oxygen before when the circulation was strong in the winter hemisphere, higher atomic oxygen in the winter hemisphere. And as the circulation weakens, we will have more atomic oxygen at equatorial latitudes, which we do not want. So we need additional momentum forcing if we want to use the correct lower boundary in the thermosphere models. So I'll next move on to my second question that I posed. So the turbulence is also important, as I mentioned earlier in this presentation, and this turbulence can affect the upper atmosphere. What I specifically focus on is non-uniform turbulence. And this is the first study, to the best of my knowledge, to understand the impacts of non-uniform turbulence on the IT system. So the gravity waves, as most of us would know, some of us don't know, but these are basically the waves that are generated because of a change in the pressure balance between gravity and the pressure gradient force. So we have large molecules here near the surface, as I told you guys before. So this leads to an overall pressure acting from lower altitudes to upper altitudes, whereas gravity is pulling everything down. So in an equilibrium state, both of these forces are in perfect balance. But if there is a slight change there's a slight change in any of these pressures, basically if there's a slight change in the pressure gradient force, for example, because of the topography of the Earth, or because of thunderstorms or convection, an air parcel can lift up, which will lead to gravity acting as the restoring force. This is similar to how we basically understand simple harmonic motion, or basically any of the motions that can generate waves. These gravity waves can be visualized at certain times as small-scale structures in clouds. And these are generated in the lower atmosphere by volcanoes, cyclones, thunderstorms, by a variety of mechanisms, basically, and they propagate up. And as they propagate up, they can interact with other waves as well. They can also interact with the background atmosphere, changing the circulation also. But the focus of the study is the turbulence that is generated by the gravity waves in the MLT region. And this turbulence is basically then feedbacks into the thermosphere and ionosphere. So as we move higher up in altitude, the amplitude of gravity waves increases. At about 100 kilometers, which is the MLT region, the gravity wave potential energy is quite high, which can lead to braking, which might result in the turbulence. And the way we define turbulence is basically generation of the small eddies. I would like to give a small example. So if you put sugar in your tea and just wait for the molecular diffusion to automatically diffuse the sugar throughout your tea, you will wait for days. But if you use a teaspoon and stir the tea a little bit, you'll generate eddies, which will result in quicker transport of sugar throughout the tea. So turbulence is a very effective mechanism of mass transport and heat transport. So the effect of turbulence on the upper atmosphere is it decreases the temperature because it diffuses the heat throughout the region. It also mixes the thermosphere. And by mixing, I mean it acts against the background state. So in the thermosphere, if you remember, atomic oxygen, the mixing ratio of atomic oxygen increases. So turbulence will try to decrease that, whereas the mixing ratio of nitrogen decreases. So turbulence will try to increase that. So it acts against the background state. So overall, the effect of the turbulence depends on the background atmosphere, but majority of the time, according to the literature, we see that O to N2 ratio decreases. So O decreases and N2 increases. So this ratio decreases. And since it's of such small scale, it is usually parameterized in most of the models through a parameter called eddy diffusion parameter. It's used in the continuity equation and also the temperature equations. It's the variation of eddy diffusion with seasons, day of the year, has been debated and studied really well by lots of studies. People usually, I guess, lots of people have seen higher values during summers as compared to winters. So this also has a semi-annual variation to it. Whereas the the spatial variation of eddy diffusion is relatively not understood well. So most of these studies that calculate the global averages just assume constant value throughout the globe. But because of the SABRE observations and lots of other model studies, we know that it's not the case. There are many small-scale structures that persist in the MLT region that need to be taken care of. So this is just a video from one of the model simulations. This shows the gravity wave structures lower down in the atmosphere. This is not the MLT region. So it just shows propagation of gravity waves with time. And this is in the MLT region. So we see that there are many small scale structures and turbulence is not at all uniform in the MLT region. So it's very unlikely that the global constant value of turbulence in the MLT region would be appropriate. And also, so that was from a model simulation. We also have measurements from SABRE. Here, the plots show the gravity wave activity from 2 studies in the past. And they show that the gravity wave activity changes with season and also has a latitudinal variation to it. And same goes for the other study too. So since my goal is to understand the impact of the spatially varying turbulence in the MLT region on the upper atmosphere, I decide to introduce lower boundary conditions on the eddy diffusion parameter such that it has a latitudinal variation to it. And this latitudinal variation is inspired from this particular study. So during equinoxes, during March, I use a latitudinal band, a turbulent latitudinal band at lower latitudes. During solstice conditions, I use this configuration where I have larger values at polar latitudes and lower values at equatorial latitudes. I guess this is another simulation where I just wanted to see the effect of high polar eddy diffusion. And the results are as follows. So during March, when I have large turbulence in the at lower latitudes, and I see a decrease in O2N2 ratio and TEC. So decrease in O2N2 ratio and TEC is expected. But what is interesting here is that the differences are actually pretty low. They are within 5 to 8%. But an important observation here is that it introduces spatial variability, even though the average change is pretty low. If I look at another simulation where I had larger values over high latitudes, during one of the seasons when the Northern Hemisphere is in winter, I see a decrease again in O2N2 ratios and TEC. TEC is actually the electron content, which I mentioned in the beginning of my presentation. So but the differences are smaller. And the reason why they are smaller is because the area of the turbulent patch at polar latitudes is smaller as compared to the area at equatorial latitudes. Now, if I look at June, which is the summer in this region, I see an opposite variation, which is pretty cool because this is totally not what I expected. I see an increase in O2N2 ratio and an increase in TEC. The differences are small, but it's interesting to understand why this is happening. So the reason why it's happening is because of this circulation that I mentioned you before. As we learned before, the summer to winter gradient in temperature can lead to meridional circulation. So during this time, this hemisphere, the winter hemisphere, will have larger O2N2 ratios. And during summertime, the O2N2 ratios will be small. So these are the background conditions, right? When we introduce turbulence, it acts against the background state. So it tries to increase the O2N2 ratio. And here in the winter hemisphere, it tries to decrease the O2N2 ratio. When I use a bunch of turbulent patches throughout the globe, I see a very large decrease in both O2N2 and TEC. This is because the area of the equatorial patch is much larger and will overtake any of the changes that are introduced by the winter patch, by the summer patch. But what we see is that there's a larger decrease in the winter hemisphere, and turbulence can act in patches and produce significant impact. So you need not have like consistent turbulence at a certain location. You can have intermittent patches, and that they will be able to produce significant impact on the thermosphere as well. So my conclusions from this study were that it introduces spatial variability, the non-uniform turbulence. The overall impact on the globally average quantities is within 5 to 7%, and it depends on the area. And it's larger when turbulence is introduced at the equatorial latitudes. The impact of turbulence is larger in the winter hemisphere. In the summer hemisphere, we see an opposite change, and it can act in patches to produce a significant impact. So I'll try to conclude everything in this section. These were the conclusions from my first two studies. I looked at the impacts of opposite latitudinal distribution of O on the ionospheric and thermospheric system. I see that it affects the thermospheric densities on short and long time scales, like the semi-annual variation. This interaction is dynamic and can change the pressure gradients, winds, temperatures, and thus the density of all species. And using saber-like atomic oxygen from VAC-MX reduces the gradients and improves the agreement with the GUVI observations. However, there is an accumulation of O at low latitudes, which reverses the phase of the semi-annual oscillation, which needs to be corrected by introducing additional mechanisms, additional momentum sources. Some of the future work that should be done is we should investigate as to why there is a summer maxima in the MLT region, which is opposite to the previous assumption. We should also look at these additional momentum source terms that will be required to correct the phase of semi-annual oscillation, because literally nobody knows about this, and this is a new result, and this should be investigated further. And the next conclusion is that non-uniform turbulence introduces spatial variability. It changes the oxygen, the nitrogen, temperature, and winds. I do not show them in the study. I do not show them in this presentation, but here I only show the impacts on O2, N2, and TEC, but it does impact the whole thermospheric dynamics. The net change is within 5 to 8%, and it depends on the area of the turbulent patch. Large change in the winter hemisphere and opposite variation in the winter and summer hemisphere. Future work should include basically introducing a gravity wave parameterization scheme in GITM, because these are very small scale structures. So it's impossible to basically have like a very small grid. It will take a very, very long time to solve the equations of the thermosphere and ionosphere. So the parameterization scheme would help in capturing these effects in the thermosphere and ionosphere. Another, I guess, important thing that needs to be done is to use SABRE data to actually determine the spatial variation of turbulence. That's it. Thank you.
Thank you very much. That was very good. I think that we're all clapping.
Okay.
Okay, so we will open. Yeah, there are people clapping there. Awesome. We'll open it up for questions for people who are not on the committee, so non-committee members. If you have a question, you can either say that you have a question in the chat window, or if there are not too many people asking questions, then you can just unmute yourself and go ahead and ask a question.
Hey, Garima. This is Brandon.
Hey.
Hey, could you show the O to N2 like plots that you showed where you basically started to add in the SAO variations at the lower boundary? Just wanted to see that again.
Okay, yeah, let me go back. These ones?
Yeah. And then could you slowly like go through that again? So what I was understanding is that as you basically, you were changing the lower boundary condition of O, right?
Yeah.
And so it's completely out of phase. So what are you suggesting is like wrong? If you're correcting the densities for O, what's like really going on? Why wouldn't this be improving, I guess?
So I guess my main point here was that the older boundary condition tries to already reinforce what we see in the upper atmosphere, the equinox maxima. So even though it's not correct, it gives us the good results because it uses EMSIS, right? EMSIS is an empirical model. Mm-hmm. Even though it's an empirical model, it mostly has observations from higher altitudes. It does not have observations from the MLT region, because the SABRE mission was not launched at the time this EMSIS was made. So it basically reinforces already what we see, so we get the right results, but it's not the right boundary condition. So answering your question as to what might be going on, was that your question?
Yeah, basically, yeah. So if you're correcting the O, it seems like something else has to be wildly going wrong, right?
Yeah, so it means that there are additional mechanisms that we didn't know about that need to be also introduced in the model. And that's what I mean when I say that either the meridional, there need to be additional momentum sources to increase the meridional circulation if you're using the right boundary. So you need to do that, or you also need to improve the estimates of the lower thermospheric dynamics, because as I saw, using the nudged simulation improves the phase a little bit. And then I introduced this seasonal variation and eddy diffusion, which also decreases this phase a little bit even more. So maybe a combination of these things can help, but it's interesting.
Okay, I understand. Okay, thanks.
Yeah.
It's like getting the right answer for two wrong reasons. And then when we correct one of the wrong reasons, we then get the wrong answer. Right?
Yeah, that's exactly what that's what I was saying. And I'm guessing that's the motivation for the third study that you were talking about, was maybe, so I'm assuming all of this was done with some flat eddy diffusion, right? So if we gave some varying eddy diffusion, perhaps that could also improve this, since you already showed like that orange line is affecting it pretty largely.
Yeah.
Okay, I understand. Thanks.
Other questions?
Ask me questions, people.
Okay. So if there are no other questions, or if you want to send Garima a question over email or something like that, fantastic. Then what we can do now is ask everybody to go ahead and leave, except for the committee members and Garima, and then we will start asking questions to Garima in private. So thank you all very much for attending.